when people saw that in the fall semester, I gave them that problem as a divide and conquer exercise to do max sum subarray in a circular array. I never knew it was on LeetCode. I thought I'd come up with it. But then somebody else has now pointed out it's on LeetCode. It's not original. Okay, that's not terribly surprising. But the students, Sarah for one, and a couple of others, pointed out, oh, well, you can do this by, you can solve max sum subarray by observing that if the max sum subarray doesn't wrap around, then you just call the normal procedure, the normal code. So it finds the max sum subarray that doesn't wrap around. And if the max sum subarray does wrap around, then, oh, so this is, wait, which camera is this? Yeah, this is the new camera. Okay, good. So if it does wrap around, so if this is the max sum subarray, so I'm just going to have this in shading. It's black. So this is so this is max sum subarray. Then she observes that this part is the min sum subarray. So which you can find by taking all the weights in the array, all the elements of the array, multiplying by -1. So the min sum subarray becomes a max sum subarray that doesn't wrap around, and calling the code you just wrote again. And I thought, oh, that's cute. So that's also on LeetCode. That turned out not to be original. I mean, there's nothing new under the sun. But this is, then later I realized I should have used this to teach reductions, because that's a reduction. You can reduce finding the max sum subarray in a circular array to finding the max sums in the normal case. If it doesn't wrap around, it's the same. If it does wrap around, you just multiply -1 and call the code again. So I thought, oh, okay, you can reduce max sum subarray in a circular array to max sum subarray. And obviously, if you have, so this is the reduction. So this is reduce from max sum subarray to, so it's reduced from this to max sum subarray circular array. And then, can you still see this? Yeah, okay. So obviously, if you have an array and you already have code that will do max sum subarray in a circular array, yeah, so I need you to get this. Can you see this? Yes. Then you have code that will do that, and now you want to find the max sum subarray that doesn't wrap around. Then all you have to do is paste on, actually only one of them. Yeah, you don't even have, you paste on sort of a minus infinity on one end. Or what it can be is something that's minus, if you don't actually have infinity, then what you can do is in here, if this is A, so this is A1 to AN. So in A0, you paste minus sum over I of AI, plus 1, putting this all in brackets. So this thing if you take this element in any subarray that wraps around, it will more than cancel out all of the others, all of the sum of everything else. So this cannot possibly be in a max sum subarray. So max sum subarray cannot possibly wrap around. So then if you have code that will do max sum subarray in a circular array, by just adding one element, you can use it for max sum subarray in a normal array that doesn't wrap. So this is reduce from max sum subarray circular array. So this is from to max sum subarray. So that means I can reduce from this one to this one, and I can reduce from this one to this one. So I have max sum subarray and max sum subarray circular array, and I can go from one to the other or back. And this is a linear time reduction. And this is actually, well, yeah, okay, you have to sum this up. So this is also a linear time reduction. So at that point, we had only seen an n log n time algorithm for this. Right? So what that would mean would be, so we knew that this was O n log n. So because we could take an instance of this problem and turn it into an instance of this problem, which was the same size, or essentially the same size, two instances actually, was in linear time, and then we could solve this in n log n time, then that gave us an O n log n time solution for this one. Right? Just, we didn't have to do anything new. We didn't have to write any new code except like 3 lines to do the reduction. But just having a solution for this, we got a solution for this one. So it was code reuse, which you actually see in software engineering. And this is actually a big chunk of how people solve problems. It's not they do it from scratch, but they realize that it's actually another problem with a couple of few little changes, and so they just do a reduction. So this is actually something people do all the time. And it's something that it's not NP completeness and you only need it for proving lower bounds and stuff like that. No, it's something useful, but it's also something we need for complexity. So, but the other cool thing is, if we can observe that suppose we get a faster algorithm for this. For example, suppose we get a linear time algorithm for this, which we just saw in one of the lectures on dynamic programming, because you can do a linear time algorithm for this. So this means that it's O of n log n. That's true because it's big O, but it's actually O of n. And in fact, I'm going to put it as a question on the homework of why is it theta n? So you actually get an advantage because I'm telling you how to do all the homework questions for assignment 3. So this is actually theta n. It's theta. It's because it's big O of n, because we now have a big O algorithm, a linear time algorithm, and it's big omega because you actually have to look at all of the entries. You need to at least read the input, all of the input. So that combined, and here too, you also need to read the input for this, because if you skip one of the cells, then I can put some huge weight in that cell. and you should take that. So because of this, getting this linear time algorithm immediately gives us a linear time algorithm over here, and then because we have this, you have to read the input, you get a tight bound for this. So that's how you can relate one problem to another problem via reductions. So that's sort of how to get how an upper bound for one gives you an upper bound for another one. But then the flip side to that is if you have a lower bound for one. So if you have some problem, so for example, if I didn't know that this, I had to read the whole thing. If I forgot that argument that I have to read the whole of the input. So I don't have a lower bound on this. But for somehow I've heard that this cannot be done in faster than linear time, and I have this reduction, then it gives me a lower bound on this. Right? So if I have a problem A, and I can turn problem A into problem B. So I can reduce I can reduce from A to B, say in polynomial time. Suppose I think there's no polynomial time no, let's say no, I don't think. I know, but for most of the time I don't know. So I know there's no polynomial time algorithm for A. So this plus this plus this equals I know polynomial time so suppose I can reduce from A to B in polynomial time. I know there's no polynomial time algorithm for A. Then I know there's no polynomial time algorithm for B. Because if there were a polynomial time algorithm for B, then it would give me a polynomial time algorithm for A. What? I'm given an instance of A. In polynomial time, I convert it into an instance of B. Then I solve the instance of B in polynomial time. And that gives me a solution for the instance of A, which is in time a polynomial composed with a polynomial, but a polynomial composed with a polynomial is still a polynomial, so that just gives me a polynomial time algorithm for A. Right, where you say, okay, you do A to B. Right, so this is the reduction. So I'm given an instance of A, say x. I reduce it I reduce X, turn X into an instance of B, and then I do alg for B, and this, so assuming that my problems are yes/no problems, right? So that's what we're going to do in incompleteness, is just decision problems. You say yes or no. So this is what, now, we don't know that there's no polynomial time algorithm for SAT. There could be, that's this whole P versus NP stuff. But we strongly suspect there is not. It would be really weird if somebody could find one. And we've been looking for 40-something years, 40, 50 years, and we haven't found one. So we just suspect there's no polynomial time algorithm for A, and that way if you can reduce for SAT, and that way if you can find a polynomial time reduction from SAT to your problem B, then it's good evidence that there's not going to be a polynomial time algorithm for your problem B. So this is how people usually teach reductions, but you can they still make sense in terms of stuff in this polynomial time, max sum subarray to max sum subarray of a circular array. So there was at some point in the lecture, I drew a map. So I was saying the most interesting thing in this course is not solving individual problems, it's understanding how problems relate to each other. Because in the first lecture, when I was saying we can find Eulerian cycles in polynomial time, really easy, it's like linear in the number of edges. And then we can't find Hamiltonian cycles. We don't, in polynomial time, we don't think there is an algorithm. So neither of those statements by itself is that shocking, right? We can't do it. We can do this, okay, well, big deal. We can't do this, okay, well, big deal. But we can do this, and we can't do this other thing, which looks almost the same. So you can find a path, you can determine if there's a path that crosses all the edges. That's easy, and we've been looking for hundreds of years, and we don't know how to do it if you just say, instead of crossing every edge, visit every vertex. So you have two problems that look very close together, but they're actually measured by their difficulty, they're very far apart. But then we're going to see in this course that problems which look further apart, for example, three-colorability and Hamiltonian path, don't look as close as a Eulerian cycle. Eulerian path, Eulerian cycle, and Hamiltonian path. Hamiltonian cycle, whatever, say. But actually, if you can find a polynomial time, we're going to reduce three-colorability to Hamiltonian path, and we're going to be able to reduce Hamiltonian path to three-colorability, both reductions going in polynomial time. So if you could find a polynomial time algorithm for one, then you automatically get a polynomial time algorithm for the other. And in fact, you can show that there's this broad, big class of problems which all polynomial time reduce to each other. And in fact, all problems that have certain characteristics all reduce to SAT. So there is a broad class which are not just one by one, but they're sort of formally all equivalent up to polynomial factors. And that's sort of the coolest thing in the course. So I was saying, okay, so we have max sum subarray, and we have max sum subarray in a circular array. And we can show that these go back and forth. And then we had like two colorability. And we had Eulerian cycle. in the lecture on coloring, I mentioned this thing that you can always, not if it's planar, but if it's not planar, so you can, if somebody gives you a graph and asks, is it k-colorable? And you have an algorithm for k+1 colorability, then you can reduce k colorability to k+1 colorability, not planar, because you have your graph G. So you want to know, is G k colorable? So but you have an algorithm that does k+1 colorability. So what you can do is add this vertex V, make it incident to everything in G. So now call this G prime. Well, if G is k colorable, then G prime is k+1 colorable, because you k color G and you have one color left over for V. And if you can k+1 color G prime, then you can color V, and then, so it's if and only, so if G is k colorable, then G prime is k+1 colorable. If G prime is k+1 colorable, then yes, G is k colorable because you k+1 color G prime and then you rip V off. And this had to be a different color than all of these. So this was your extra color, so this is now k color. So it's if and only if. So this, you can answer, oh no, I can. So you can reduce k colorability to k+1 colorability, but not backwards in general. Oh, somebody just paid money. I feel bad about that. Sorry.
I don't think anyone paid money. So that said that there was a 40-minute time limit, and then it said, well, we've removed the time limit.
Yeah.
Oh.
Yeah, I
Zoom's starting to
think
do
Zoom
that
does
now.
that automatically.
Oh, good. Okay, so now we do. Good.
Quick question, just while we're pausing, if you don't mind. I had a quick question.
Yeah.
When you were going from MSSA and like reducing it to MSSACA, that the reason why it's ON to reduce it, is that because we're summing all of our entries and then taking the negative of that and adding that to the end?
Yeah, yeah, we're going from this one to this one. I'll move this over here just in case. This takes linear time because, yeah, you sum everything up. If you could add negative infinity, then I guess.
Yeah, that was mainly my question.
Would it be constant time? Yeah, maybe. But then in that case, I mean, in this case, you sort of have this lower bound that you have to read the input. Because, okay, if this takes all one time, then if you found a sublinear algorithm for this, so there are certain problems where you can actually talk about, you don't have to read the whole input. They're kind of weird. So if anybody's, it used to be still is a popular field about sublinear algorithms, where you can sort of probe, and usually this is randomized. So if you could find a sublinear algorithm for this, then I guess that would imply that you would get a sublinear time algorithm for this as well. But in this case, you actually do have to, for both of them, you have to read the whole input. So it doesn't really help you that this can be faster than ON. So yeah, the reason I was sort of skimming over that, I hadn't really thought about it it being faster than linear time, but I guess it doesn't have any weird implications. Yeah, I would be careful. If I got a sublinear time reduction, maybe it made me cautious. But for the moment, let's just draw these arrows in when you get, say, a polynomial time reduction. So you can go from two colorability. My pen! Ah. I wonder if you can buy lone black pens from Staples. These came to pack. So you can reduce it to, okay, so I'm going to make this longer. Where is my, okay. So by this, I can go from two colorability to three colorability. That's not right, all of colorability. So to three call. And then, by the same argument, I can go from three call to four call to five call, etc. But I can't go back. Okay, if these are polynomial, if these arrows mean polynomial time reductions, we don't think there is a polynomial time reduction from three colorability to two colorability, because we can do two colorability in polynomial time, right? It just is a graph two colorable. Pick a vertex. Well, first of all, you only have to consider connected components, so pieces that are connected. Because, I mean, if you can two color all the connected components, then you can two color the graph. So choose some connected component. Choose a vertex. Okay, that's white. And then everything that all of its neighbors must be black, all of their neighbors must be white, all of their neighbors must be black, and so on. And if you ever get something which should be black and white at the same time, then it's not two color. Right? So this is just like breadth first traversal. So you can do this in essentially linear time, in linear in the number of vertices and plus the number of edges. But we don't think there's a polynomial time algorithm for three colorability. We've been trying for decades and never found one. So we don't think we can go backwards. Now, it turns out that three colorability, we can go, there is a polynomial time algorithm that we haven't seen yet. So I'll put that in red. It will turn out that you can actually go from four colorability and five colorability to three colorability. It's not quite this easy, but you can do it. It's not the same graph. It's not, I mean, the graph changes. And you have to pull some tricks. But you can do that. So I forget, what other problems did I make? Oh yeah. So we had, I mean, this would be stupid. Ever reducing two colorability to three colorability. Why would you ever do that? If you have a problem you can solve and you turn it into a problem you can't solve, that's not useful. But you could. So yeah, I'm going to avoid the black marker. So I forget which other problems we had before. Oh yeah, so we can also do planar two colorability. You can do this trick to reduce planar two colorability to planar three colorability, because if you glue a new vertex on and you make it incident to everything else, in general that breaks planarity. But it turns out this is a sneaky. It turns out that so the red arrows are for things which are not that easy. So over here we have planar three colorability. And you can actually reduce planar 2 colorability to planar 3 colorability in polynomial time. But again, it's not easy. It's not as obvious. But then you have planar 4 colorability. Well, and you have planar 5 colorability. Well, in the lecture on coloring graphs, I said that there's this 4 color theorem. Planar graphs are 4 colorable. So if you're given a planar graph, you can just check, is this a planar graph? There are actually algorithms to check planarity in polynomial time. And if it is a planar graph, then it is 4 colorable. So as long as the input to this is actually a planar graph, the answer is yes. And then if you can 4 color something, you can 5 color it because 4 coloring is a 5 color. You're just not using your 5th color. So the answer, basically the answer to this is yes. And the answer to this is always yes, as long as the input is well formed in a planar graph. So this is easy, and this is easy. This one is hard. This one is easy, but not always yes. This one is easy, but essentially always yes. This one is easy because it's essentially always yes. This one we don't know how to solve in polynomial time. It turns out that, well, you can do these reductions. You wouldn't want to, because you're taking a problem for which the answer is always yes, and you're turning it into a problem that you don't know how to solve, but you could do that. It's not, I mean, you could just, take this, check that it's a planar graph. If it is a planar graph, then turn it into a graph, a trivial graph, which can be 3-colored. And if it's not a planar graph, turn it into a graph which is not 3-colored, for not 3-colorable, for example, a 4-cleat. And then here, if it's a planar graph, turn it into a triangle, and if it's not a planar graph, turn it into a 6-cleat. Okay, so then this is where I'd like you to do something I didn't do in the lecture. You can find what's called a gadget. So for doing reducing planar 3 colorability to 3 colorability. Okay. So what it is, if you search for it, it's on Wikipedia, and it's a little diagram that shows how to take an edge crossing and replace it. So if I give you a non-planar graph and I ask you if it's 3-colorable, what you can do is take every edge crossing and replace every edge crossing by an instance of this gadget. And this turns the graph into a planar graph such that the resulting planar graph is 3-colorable if and only if the original was 3-colorable. Okay, so what it will do, if you put in that gadget, it will be showing, well, okay, for one thing, planar 3 colorability obviously reduces to 3 colorability, right? I mean, if I give you a graph and I say, is this an instance of planar 3 colorability? You can say, well, and you know how to do 3 color, and you have some algorithm for 3 coloring where you have a magic box that solves 3 coloring. Then you'd be like, is this a 3-colorable planar graph? Well, is it 3-colorable? You ask the magic box. And is it planar? Well, I just told you there are polynomial time algorithms to check planarity. So this reduction is not bad. And then I'm going to still draw this in red because this gadget is not that, it's not that bad. And so this is, I'm going to like sneak in a sort of first not easy reduction. This also goes like this. And because this reduces to this, you also get, from what I said about 4-coloring reducing to 3-coloring, but not easily, you also get that 4-coloring reduces to planar 3-colorability and 5-coloring reduces to planar 3-colorability. Because these arrows, because the composition of two polynomials is a polynomial, these arrows are transitive. So I can go from 5-colorability to 3-colorability, and then I can go to planar 3-colorability. Again, this reduction is not that easy. So we start getting this network. Let's get this out of here. This network where if you get an algorithm for example, if you somehow got an algorithm for 4-colorability, then it would give you a polynomial time algorithm for 4-colorability. It would give you a polynomial time algorithm for planar 3-colorability. Right? Because if I had an instance of planar 3-colorability, I can check linearity in polynomial time. I can also do a reduction to 3-colorability. I can reduce, and then I can reduce that to 4-colorability. So I take my instance of planar 3-colorability. It's already sort of an instance of 3-colorability. And then I reduce it to 4-colorability, and then I have an algorithm. So if you have this connection, this network, and you get a solution for one thing, that solution sort of spreads out. Okay? And the same thing, if you could show that 4-colorability is hard, then it would imply that planar 3-colorability is hard. Because because you can also reduce not from what I just said, because that would be backwards. Not because you can reduce planar 3-colorability, because showing that planar 3-colorability is hard does not imply that planar 2-colorability is hard, because planar 2-colorability isn't hard. But if I can show that 4-colorability is hard, then it does imply that planar 3-colorability is hard, not because I can reduce from this to this, but because I can reduce from this. This is where you get backwards. Because I can reduce from this to this, if this is hard, it means this is hard. Yes, because if this is hard, and I can reduce from this to this, if this were easy, then I could solve this one by turning it into this and solving it. This is why you have to be a bit careful. Now there are problems which are like way harder. There are problems which you cannot solve. There's the Entscheidungs problem, the halting problem, and I will try to show that at some point in this course, even though that is not actually really part of this course. But it is not possible in any amount of time. And we can prove that. There are problems which you can show we can do, but they're like p-space complete or something. So we know that there are no polynomials like that. So the interesting thing is, if I draw a line between the stuff that we know how to do so on this side are the things that we know how to do in polynomial time, and on this side is stuff that we don't know how to do in polynomial time. But it turns out that all these problems, they're all equivalent, and it turns out that there's this other big class where we don't know if we can do them in polynomial time, but if we can, then we can do all of them in polynomial time because the network, they're all connected. So that's sort of getting ahead, but is there anything else I wanted to? Oh wait, well, okay, and then there's this other stuff which is harder. So this class, there is this class I know which is NP, and so the question is there actually a polynomial time algorithm for this? Where if you could, so if you could find a polynomial time algorithm for one, you sort of get over this mountain range or over the ocean or something like that. This is, you get around some barrier and then, you know, you can reach one of them and then this whole area becomes reachable. So it's like the map, the geography of problems. And there are now thousands of these, which are natural. They're not all graph problems. They're string problems and logic problems. And oh, so my brother, where did it go? Oh, yeah. So in the lecture, I was showing, I was talking about this copy of this book, which I got my brother to actually ship to me because his company makes face masks, and he sent me face shields, and he sent me a face shield, and he shipped this. So this has hundreds of problems, matrix cover, fault detection in logic circuits, decision tree, permutation generation, decoding of linear codes, okay, equivalence of simple functions, cosine product integration, comparative vector inequality, staff scheduling, job shop scheduling, two processor flow shop scheduling with bounded buffer, sequencing to minimize maximum cumulative cost, serialization, serializability of database histories, Tableau equivalence, rectilinear picture compression, consecutive block meaning, consecutive sets. I mean, there's shortest common superstring, that is a really famous one. Shortest common supersequence, longest common subsequence, bounded post-correspondence problem, hitting string, bin packing. There are hundreds and hundreds of problems. Most natural problems that we've been studying for years, either we have a polynomial time algorithm for them, or most of them are this NP complete, and they're in this class where if we can solve one, we solve them all. And that's sort of what I think is the most important part of computer science, is this idea that you can study, instead of studying problems in isolation, in which case you're missing the forest for the trees because you're studying each tree by itself. It's like, no, the whole is greater than the sum of its parts, and any one of these problems is by itself like not that interesting, but oh, actually, maybe people are you emailing me to tell me to shut up or something? Oh no, I can, okay, probably not you because that's through Facebook or Messenger or whatever. But the thing that's interesting is, so why do people in one area of computer science who are doing databases, why would it be a huge deal to them if somebody figured out how to find color graphs in polynomial time, to determine whether graphs were five-colorable? Well, because that would rock all of computer science. People who don't study graph theory would still be stunned, because there are tons of problems in databases which can be, through this network, can be reduced to five-colorability. So a result in one area of computer science can actually provide hardness results or algorithms, upper bounds, lower bounds, or upper bounds for other areas of computer science. So that's why you get, if somebody solved this, also all the database theorists would be out in the street party. Solve this in polynomial time. So, and And so in matrix multiplication, why do people like, oh, wow, we've reduced the coefficient, the exponent in matrix multiplication? Well, why do people get excited? Because there are a lot of problems. It's an important problem by itself, and a lot of problems can be reduced to matrix multiplication. So speeding up matrix multiplication automatically, in theory, speeds up our solutions for those problems as well. So I think that should definitely be enough for scribe notes. I can send you a link for this reducing planar three-colorability to three-colorability. But also, if you just Google it, it's on Wikipedia. I mean, if you just do a Google image search, then you'll get it. It's just if you can like paste it somewhere in the notes. Even though I didn't talk about it in the original lecture, which is that's going to confuse people. I forget if I talked about other problems. As I said, there are problems which are harder. I mean, this is not the whole map. Oh yeah, I also said this is just time. I mean, this is the map for time. But there is also a map for space complexity. So in the fall semester, one of the first algorithms I introduced is interesting because it's about space. It's about finding frequent elements using very small space. It's in the notes for the fall course, but it doesn't really fit this time. So there's maps for space, there's randomization. But this is probably the most sort of famous map, and I can send you, if you do a search, you can also get, there are famous drawings of this where you sort of have P. So this is P, and this is NP, and we don't know if these two are equal, and this is co-NP, and then you have other stuff, you have this map of complexity classes, so you have like RP, which is randomized, and then you have, I think RP is randomized with two-sided error, and then you have, oh, it's been so long since I did this stuff. Like BPP is one-sided, so ZPP is zero-sided, so it's like nothing. Okay, but don't put that in. Don't put in that I forget the difference between RP and BPP. One of them I think is one-sided error, and one is two-sided error. Wow, it's been like nearly 20 years. So you can find this picture, which shows co-NP we're not going to see. Okay, NP we're going to see later in the course. But this is sort of the drawing of the landscape of this. This is sort of a drawing of how we think this map is. It's sort of like the lakes and mountains and geographical features of computer science. And so, even though most of us don't work on this insanely hard stuff, it's really important just to be educated computer scientists that we have some idea of what's out there. I mean, I've never been to Australia, but I know roughly where it is, and I know some stuff about it. And if somebody said Australia and I had never heard of it, then they would think I was really ignorant. And and it's the same thing. Even if we end up doing, most of us end up working in polynomial time stuff and fairly easy polynomial time stuff. But still, it's important to know sort of at least a rough idea of the geography of our own field. And now I'm sort of getting philosophical. So, yeah. So oh, the last thing. I sent you a link to something because people generally, these polynomial time reductions tend to go from, well, they go sort of this way. So we don't know if, notice all of the polynomial time reductions are going this way, because if there were any arrows going this way, then if there were any polytime reductions from something on this side that we don't know how to do in polynomial time to this side that we do know how to do in polynomial time, then this line would disappear because we could do this stuff in polynomial time by reducing it to whatever to look. If there were an arrow from 5 colorability going to Eulerian cycle, then I can do this in polynomial time. I could do this polynomial reduction. I would get all of this stuff in polynomial time. This line would move over here, this green line. But the thing that I want people, I'm not sure if this is too much to ask. So one of the recent trends in theoretical computer science is this stuff called fine-grained complexity. And it's actually, I can't draw it on this picture because these arrows are polynomial time reductions, and this is a super polynomial time reduction. So there's this problem called SAT, which is given a Boolean formula, is it satisfiable? Yes or no? And so you can relate it to a problem for which you can reduce it to a problem for which SAT is actually sort of the canonical NP-complete problem. Don't worry about what NP-hard and NP-complete and NPs and the difference between NP-complete and NP-are. I mean, if you want, you can read it on Wikipedia. But that's going to be for way down the line in the course, like after the midterm. But so there's this. So this SAT is sort of the canonical problem, NP-complete problem. So given a Boolean formula, let's say 3 SAT. So Boolean formula in disjunctive normal in conjunctive normal form, 3 conjunctive normal form. Just in case. So there's this problem called orthogonal vectors. So orthogonal vectors is given given 2 groups. So this, I've just been talking for a while. Yeah, because that cutoff was after like 40. Oh, I've been talking for an hour. Okay, I'll just say this part, because this is kind of cool, and I want people to see that this stuff is more complicated than you might think at the beginning. Okay? So orthogonal vectors is you're given 2 sets of binary? Maybe this works. Maybe this works even with binary. Just binary. Okay, so you're given 2 sets of, binary vectors in this case. So in general, I mean, it's harder, but let's say you're given 2 sets of binary vectors. So you have this set A. So you have a set of binary vectors of so there's sets of binary d-dimensional vectors. Okay? And orthogonal vectors asks you, is there a vector in A? Can you choose a vector x from A? And a vector y from B such that x dot y equals 0. So x and y are orthogonal. That's it, right? So these are d-dimensional vectors. D is not that big, say. Okay, so generally these are pretty big sets. Say they're n. D is, let's say, much smaller than n. We're gonna sort of ignore D in a hand waving way because I didn't actually practice this before this meeting. But the question is, suppose that there are, say, n1, I forget, well, let's just say that there are n vectors here and n vectors here. Okay, so this orthogonal vectors so this is the orthogonal vectors problem, is to ask, is there an x and a y, an x in A and a y in B, such that x dot y is 0, x and y are orthogonal? Well, you can do that in basically quadratic time, right? You just take every vector in A and multiply it and take its dot product with every vector in B. And okay, so it takes like d time for each product. But ignoring the d, this takes quadratic time, right? Yes, that's the binary vector, either 0 or 1. So now I have to remember the reduction. So somebody actually asked this in the fall semester. I was showing all these reductions, and somebody said, are there reductions which take more than polynomial time? And I said, yes. But it doesn't, but then the implication, if you had a super polynomial reduction from something over here to something over here, and then it doesn't imply that you get a polynomial time algorithm for this, because given this, reducing it takes super polynomial time, and you can get something which is super polynomial size. So then you have a polynomial time solution here, but a polytime solution in something which is now super polynomially bigger. The composition of a polynomial is something bigger than a polynomial is something bigger than a polynomial, so it doesn't give you the polynomial time solution. So the whole thing, but yes, there are super polynomial time reductions. So I'm just showing you one now. So this is a quadratic time algorithm, and we don't really know, we don't really have anything that's much better than quadratic time for this problem, okay? And there's a reduction from SAT to this, but the reduction takes super polynomial time, but it works in such a way that if you got a solution to this, which took much better than quadratic time, then it would give us an algorithm for SAT, which works in better than 2 to the n time. And this breaks something called the strong exponential time hypothesis. And so this is cool because it means that assuming stuff about hardness of these hard problems, if these problems are as hard as we think they are, it means that we get lower bounds for problems which we have polynomial time algorithms for, but we just want to know if, can we do better than quadratic time? Quadratic is already polynomial. But these super polytime reductions mean that if if SAT is really as hard as we think it is, then we can't get a subquadratic algorithm for orthogonal vectors. So, and the reduction is not that hard. So, let me just see if I can remember it. So basically what you do is, given your formula, yeah, it's not that hard. Yeah, given your satisfiable, given your Boolean formula, you split the variables into two groups. Remember, I'm trying to do this after a night where I stayed up to write a paper. So the idea is you have but okay, so it's in the link I sent. So there are some tricks. For example, things which you think should be 1 are actually, you make them 0. So basically the idea is you split it up such that it's the variables or the literals. So that you're going to generate, I think you split you split the variables into two groups. So you can check that link. You split the variables into two groups. And then you enumerate, yes, okay, here's how it goes. I hope. So say it's on n variables. This is sort of going to be related to this n, but it's not the same n. Okay. So split them into two groups. Right. Now, what you do is for each group, consider the 2 to the n over 2 possible truth assignments. Right, so if this is some binary, this is like x1 or x2 or not x3 and x not x2 or x3 or not x4. Right, so this is my formula. So I have 4 variables. No, okay, so let's say, and x1 or not x3 or x4. So I have 3 clauses and 4 variables. So what I'm going to do is take my two groups. Group A is going to be x1 and say x2. Group B is going to be say, okay, so these are my A variables. These are my B variables. And okay, so I mean, you don't have to put this in, because this is way beyond the scope of an undergraduate algorithms course. This is way beyond the scope of an undergraduate complexity theory course. I mean, this is sort of something that you only generally run into in an advanced grad course, but it is very cool. So here, if I look at 0, 0, 0, 0 does not give me, if I assign x1 is false and x2 is false, it doesn't give me the first clause. It doesn't satisfy the first clause by itself, right? Because these are both false. However, it does satisfy the, it doesn't satisfy the first clause. Yeah, okay, so it's a 3-set form. Given a 3-set, so in 3 conjunctive normal form. But it does satisfy the second clause because it's because not 2, if this is false, not 2 is true, and so this is not 2 is true, and this is a disjunction, so this clause is satisfied. Because it's not either not x2 or x3 or not x4. Well, that's true because not x2. So this is a 1, and then this one is, this one, it doesn't satisfy this. So this would normally be a 0. Now, actually, that's what you would think you would write, but you don't write this because you write a 1 if it doesn't satisfy, and you write a 0 if it does. Okay. So then there's, so let's say this is false, false. So this is for x1 and x2. False, true. False, true. I get this false. If x2 is true, x1 is false, but x2 is true, that satisfies this clause. So I write a 0. This was the bit where I said that you have to write a 1 where you think you would write a 0 and vice versa. This one, it's not true. So I write a 1 because x1 is not in here, x2 is true, so not x2 is false, so it doesn't satisfy this. But then, and it doesn't satisfy this one because x1 is false. And then true, false, it satisfies this one. It satisfies this one. And actually it satisfies this one. Okay, so this is going to be a bad example because this is boring. And then true, true. It satisfies this one. It doesn't satisfy this one, and it satisfies this one. Okay, so this is a boring example because I have a vector that's all zeros. So obviously you shouldn't have that because it's orthogonal to everything, sort of. I mean, its dot product is 0 with anything, but okay, so that's not a good example. How many things are there here? Well, this is n over 2 variables. So this is 2 to the n over 2 stuff. This is 2 to the n over 2 vectors. And then here I have the same thing, but for 3, 4. So false, false. This actually makes this satisfies this because x3 is false, and not x3 is true. But then on here it satisfies this one because x4 is false, And then here it satisfies this one. Okay, so this is again a bad example because I get something. If x3 and x4 are false, then it satisfies everything. But whatever. False, true. So it satisfies. It doesn't satisfy this because this is false, and this is x3 is false, so this is false, and x4 is true, so not x4 is false. So it doesn't satisfy that, but then false, it does satisfy this. Okay, let me just do the last part of this. True, false, okay, of this boring example. True. It doesn't satisfy this, it does satisfy this, it doesn't satisfy this. And true, true, it doesn't satisfy this, it does satisfy this, and it does satisfy this. Okay, so if I'd chosen a better example, a better formula here, then what you'd see is that this is n over two things. So these vectors say it's a 0. So in some vector, it's a 0 if that truth assignment makes that clause true. Right? So I'm considering these two subsets of variables separately. So now what I can do is say, oh, well, ignore these two all 0 vectors, which are screwing everything up. But if I could say there's some vector in this set, some binary vector in this set, and some binary vector in this set, such that their dot product is 0, they're orthogonal, then that means that for every clause, either the truth assignment to the first subset of variables is making that clause true, or in which so that you have a 0, the ith bit. So if the ith bit of the dot product is a 0, it means either the ith bit in here was a 0, meaning that the truth assignment to these variables was satisfying that clause, or the ith bit in here was a 0, meaning that these variables were satisfying that clause. So if there is a vector in here and a vector in here such that their dot product is 0, then it means that my formula is satisfiable. But now I'm reducing this problem of SAT. I'm reducing it to a problem to orthogonal vectors. But the reduction is blowing things up. And this is now not n vectors and n vectors. This is 2 to the n over 2 vectors and 2 to the n over 2 vectors. So I'm getting an exponentially larger instance of orthogonal vectors. Okay, this is too much. Okay, I'll finish. So I want them. Okay, I'll just finish up. So I just want you. People get the idea that you reduce. I just don't want you to imply that these reductions, you always just reduce NP hard problems to NP hard problems. So this, when I was drawing these arrows, you can reduce 2 caught-ability to 3 caught-ability. It doesn't make any sense, but you can do it. You can reduce max sum subarray to max sum subarray with a circular array and backwards. So you have reductions. They're not just NP stuff. So this part, this is just a reduction which doesn't work in polynomial time, but it's still interesting. So no, you don't have to put this in. Maybe if you could just, you could say a couple of words and I'll like patch it up. But so the idea is here. I get a problem. I get an instance with if I have a formula that's on n variables, I get a problem that's of size like 2 to the n over 2. Right? So I get an instance of orthogonal vectors where this is the 2 sets of vectors are like 2 to the n over 2. So suppose I could do orthogonal vectors. You know this. So now this is n prime equals 2 to the n over 2. N prime equals 2 to the n over 2. Well, suppose I could do this problem in better than n prime squared time. So let's suppose I can do it in something like, if we could solve orthogonal vectors in O, so this is n prime, but something like, let's say, n, I don't want to have a prime neck if I'm going to have an exponent. Let's say that this is m vectors and m vectors. In m to the 3 over 2, so better than n squared, then we could solve set in O 2 to the n over 2 to the 3 over 2, which is O 2 to the 3n over 4. So we could solve set in better than 2 to the n time. Wait, somebody wrote a note? Help. Oh, okay, right, sorry. So that means that we can relate by this reduction, which is a super polynomial time reduction, speeding up orthogonal vectors to be faster than quadratic time would speed up would give us faster solutions than set. So this is a polynomial time. We can do this in polynomial time. We can't do set in polynomial time, but because this is a super polynomial time reduction, this gives us an instance of orthogonal vectors, which is of size like 2 times 2 to the n over 2. We can still relate these two problems. It's not like reductions are just between easy problems, or reductions are just between hard problems that we don't care about in real life. You can have, I was really surprised when somebody told me this. And in fact, lots of people were surprised when, and now lots of people were surprised when they found out that reductions can be interesting and go this way. You can reduce really hard problems to really easy problems. You can reduce problems for which we don't have solutions that are better than to the n. You can reduce them but not in polynomial time, but you can reduce them to problems for which we have quadratic time solutions. And so, because we think that SAT takes time at least about 2 to the n, we think that orthogonal vectors doesn't have a solution that's much better than quadratic time. And I don't know, I don't want you to give this reduction. I mean, this would be like seriously horrible. I mean, it would cement my reputation as being an insane professor. But if you can think of some words to say that that reductions, you can't just say reductions go from easy stuff to hard stuff, or from hard stuff to hard stuff, or easy stuff to easy stuff. There are this weird class of new, really cool reductions which go from hard stuff to easy stuff, but the reductions take super polynomial time. But no, you don't actually have to, you don't have to do this whole thing. So this was just a summary. I sent you the link to that paper that described how to do this. So it's just like reductions are, it's like the force. It's what reductions bind computer science together, right? Don't put in that it's like the force.
It's going in there. 100%.
Yeah, it's in there, it's recorded, it's going in.
I'm supposed to avoid these culture-specific references. So, I mean, there could be students who've never heard of the force. It just makes it hard to do improv lectures. But yeah, I mean, reductions are not, I don't want them to be right at the end where people hear about reductions and NP completeness and they think, yeah, that's hard stuff that nobody actually cares about in practice because we can't solve it. Why would I ever care about stuff I can't solve anyway? Reductions are everywhere. And there is actually one of the other scribe groups already got that picture from here, the cartoon, which is easier to find. This cartoon where, yeah, here, this one, where it's these people where so in one caption it's saying, I can't find an efficient algorithm, I guess I'm just too dumb. I can't find an efficient algorithm because no such algorithm is possible. Well, that's really a hard thing to prove. I mean, but in general, that's so then I can't find an efficient algorithm, but neither can all these famous people. So that means if you have some problem. So one of the reasons the reasons that normally we teach reductions and NP completeness in this course is because if your boss gives you a problem and you work on it for 2 weeks and you're not getting anywhere, then, I mean, ideally you work on it for 2 weeks and you get a solution. But then if you work on it for 2 weeks and you're not getting anywhere, there's a fair chance that it's, I mean, it might be in that book, or it might be that you can prove a polynomial time reduction from and this is the important direction, from an NP hard problem, a problem that's known to be NP hard, to your problem. And that way you can say, okay, if I could solve my problem in polynomial time, then I could also solve this NP hard problem, like SAT or 3-colorability. So say you can show that you can reduce 3-colorability to your problem. You can show that given an instance of 3-colorability, you can turn it into an instance of your problem in polynomial time so that this instance of your problem is yes, if and only if the instance of 3-colorability, it actually is a 3-colorable graph. So that way, if you could come up with a polynomial time algorithm for your problem, you would have a polynomial time algorithm for 3 colorability, and that would be weird because nobody's ever found one. And we've looked really hard because remember we've looked, people have worked on all these problems over here, and they're all connected. And if you solve one of them, you solve all of them. And if one of them is hard, they're all hard. So the idea, if you can show that your problem, you can do a reduction from one of these problems to your problem, then that means that solving your problem would solve all of these problems in polynomial time. And then you can reasonably go to your boss and say, look, I'm probably not going to find a solution, and probably nobody else is either. And then you may get fired. But it will be unfair. So at least you'll be able to console yourself that you've been fired for not being able to do something which we don't know is impossible, we strongly suspect is impossible, and nobody's been able to do it in 50 years. So you'll probably be able to take it to like, what is it, the employment board or something like that. I don't think in the book it doesn't mention that like you can like take it to the employment board. But probably if you get fired for not solving an NP problem, NP hard problem, then yes, you can probably take it to the employment, whatever, equity, arbitration, whatever these things are. Okay, so that's the reduction lecture when I now have 2 whiteboards. You don't go into this, but just if you could like give some impression that also now it's sort of popular and stylish in theoretical computer science to do this fine-grained complexity and talk about reductions and how hard stuff can be related to easy stuff, and that means that the easy stuff is not too easy. So assuming the strong exponential time hypothesis, we now get lower bounds for edit distance or orthogonal vectors. What other stuff like tree distances and all this. So it's like there have been. So the 2 best theory conferences are Stock and Fox, and there have been dozens of papers in the past few years about proving these called fine-grained complexity results, showing lower bounds for polynomial time algorithms, assuming a strong exponential time hypothesis set. So yeah, it's just do your best. Like this is a tall order about this, but just so it started off pretty easy, like this max sum subarray, and the circular array. Just do your best, and yeah, don't put this in; it'll just confuse people. I mean, don't put this whole thing in. Just put in like a line saying there are also super polynomial time reductions, going from hard stuff to easy stuff. Questions?
Not really. I think I get like the first half of the stuff you said, and then when like this last question kind of just melted my brain. But
yeah, it's I shouldn't have done this. It's just so cool, and it's surprising that anyone would ever reduce. Like people would say, you reduce SAT to orthogonal vectors. You can't do that because orthogonal vectors is obviously quadratic time, except for like it takes an extra d times d for the multiplication, but you can actually get around that. It's sort of. So this is polytime, and SAT is the canonical NP complete problem. 3 SAT is the canonical NP complete problem. How we don't know how to do in polynomial time. How can you reduce SAT to this? because the reduction doesn't work in polynomial time. And it's just something when I was in undergrad, I would never have expected that you could do that, that anyone would do that, or that it would ever produce any interesting results. But it turns out that people are studying these super polynomial time reductions. But no, sorry, I just stuck that in. It's nobody puts this into undergrad courses. Yeah, don't worry too much about this. The main thing is like the first half.
Okay. Sounds good.
Okay, so I should maybe go and have coffee and breakfast and stuff, and like see if I've missed anything while I've slept the morning away, and hope that my co-authors have not found bugs in the paper we just submitted. Yeah. So I wanted to talk to you because like the first lectures where I was doing it with the notepad. Wow. Hello? Hello? I think I just got a delivery. Oh, right. I ordered a webcam before the faculty got me a webcam. So maybe my webcam has arrived. I should go down and see, because I don't know if but so the reason, like the first lectures where I was doing it on a notepad and like I was just talking in the chair and I didn't have the whiteboard, those are really, really bad. And then the ones where I just had the whiteboard, but I was still fighting with the iPad all the time, those lectures were really unpracticed. And they also were really bad. So now that I gave the iPad to Sarah, and I'm just fighting with webcams